everyone, I'm Norman Wahlberger and welcome to the Algebraic Calculus. Today's video is a very important one because we're moving towards setting up the logarithm in a geometrical and algebraic way which ties it very strongly to the geometry and algebra of the unit circle in the ordinary Euclidean geometry. So the theory of the circle and the theory of the hyperbola, we're kind of trying to unify them so that we get the cosine, sine, the circular functions, and the hyperbolic trig functions, and the logarithm sort of at the same time with the same technology. Okay, so today's title is Log Ladders and Lemmermeyer's Product. And what we're going to do is to start with a beautiful geometrical characterization of a structure which we'll also be able to see algebraically in quite a different way. Now, this is quite an interesting story. So as far as I know, this product which exists on a general conic is due to Franz Lemmermeyer, who in 2003 wrote the paper Conics, a Poor Man's Elliptic Curves. It's actually quite a modest title for what I think is actually a very important insight into a key structural property of conics that somehow had been missed out by millennia of investigation prior to his work. So the idea is that if you have a conic like this one, but it doesn't have to be an ellipse, it could also be a parabola or a hyperbola, and we fix a point O on it. Okay, so that's the starting point. We fix a point O on a conic. And then we're going to define a multiplication or a product for points on this conic. And it's very simple. So given 2 points A and B on the conic, what we do is we define a new point C, which is the product of A and B. And how is C defined? Well, we take the line joining A and B, and we form a second line through our fixed point O parallel to that line. And that line through O will meet the conic at a second point. Because if a line meets a conic at one point, then it will also meet it at a second point, and that second point is the product of A and B. It's a very elegant kind of thing, and in some ways Lemmermeyer shows this as some kind of analog of more complicated group structure on cubic curves, elliptic cubic curves. And it shares some of the number theoretical properties that these more complicated algebraic structures do. But from our point of view, it's this kind of product which plays a key role, has an intimate connection with the analysis centered around logarithms and circular and hyperbolic functions. Now, in this discussion, there's a certain special case that occurs occasionally that we need to point out. For example, if the point A and the point B coincide, then what do we mean by the line joining them? So if A and B are points on the conic and they approach each other, then the line joining them approaches the tangent to the limiting point. So that's motivation. So we just agree that when A equals B, then the line AB is by definition the tangent to the conic at A. So in that case, for example here, this would show you how to square the point A. There's our fixed point O, there's our point A, there's the tangent through A. So to find A squared, we just take the line through O, which is parallel to the tangent, and that's A squared. So it turns out that this product of Lemmermeyer is a group operation, so it forms a group, and the key property there is associativity. So if you have 3 points, you multiply A, B first to get a new point, and then you multiply that with C. Why is that the same as what you get when you multiply A by the product of B and C? So it turns out that the associativity is really a consequence of Pascal's theorem. And that's the most famous theorem really about conics, and going back to Blaise Pascal, who discovered it when he was a teenager. So here's a picture of the Pascal's theorem. I'm giving it to you in the somewhat non-standard view of having a hyperbola, just something different. So we have 6 points on this hyperbola. We have A1, B1, C1, A2, B2, and C2. And as this diagram suggests, it doesn't matter where these points are. Okay, so the theorem has to do with some three auxiliary points which are formed. The claim is that these three auxiliary points are collinear. They're the ones in green here. So the first one is A1, B2, which is that line, product with A2, B1. A2, B1, there's A2 and there's B1. So we're talking about the product of these two lines, this one and this one. By that we mean the common intersection. So this thing here represents that intersection. And B1, C2 times B2, C1, that will be B1, C2, there's that one there, and B2, C1, that's the line there. So this second point is that point there. And the third one, C1, A2, that's that line, and C2, A2, C2A1 rather, that's that line there, and these two lines meet, okay, off the page at some point in that direction. And if we extended our page and found the intersection of these two lines, and we had done everything neatly and accurately, then we'd find that these 3 points here are collinear. So that's Pascal's theorem, and that's really the essential ingredient in proving the associativity of the Lemmermeyer product. Now it will be useful for us to observe that Lemmermeyer's product can actually be restated in terms of what I'd like to call an integral affine structure on a conic. So I want to explain this to you. I think it's quite interesting. So to do that, let's go back to the very first lectures in this course. We were talking about affine geometry and setting that up, basically only using parallel lines. Remember, perpendicularity played no role. And with just parallel lines in the plane, one of the things that we're able to do is to translate a vector. Like this vector here, say the vector between A1, A2, let's call it V. We can translate that to here. And how can we do that? Well, we take the line that vectors are on and look another line parallel to it. And then through A1 and A2, we draw two other lines which are parallel, which meet this second black line in the 2 points B1 and B2. So this thing here, A1, B1, B2, A2, that's by construction a parallelogram. And that allows us to assert that this vector and this vector are the same. So we've been able to translate this vector to that second parallel line. Then if we do that again, let's say we want to translate this vector so that it's starting here. Well, then we just join B1 with C1, and with a parallel line join B2 with the new point C2. Essentially translating the vector now back to the original line. So after we've done that, gone up here and then back there, we've ended up translating the vector V from here to here on the same line. Translating a vector V on a line. Now I want to show you, quite interestingly, that the same kind of thing supports an affine structure on a conic. So there's actually a notion of a vector on a conic. Maybe we'll say a conic vector. And this conic vector arithmetic is such that we can add conic vectors and we can scale or multiply them by integers. So let me illustrate that with a diagram. Okay, so here's a conic, and here are 2 points, A1, A2. And we're going to regard these 2 points on the conic as forming a conic vector. We'll denote it with a V with a little hat instead of a little arrow. Okay, so let's move this vector. We're going to translate this vector. So what we're going to do, very parallel to what we did over here, we're going to draw in some other direction 2 lines, maybe this one here, and then parallel to it, another line through A2. Okay, so now we have 2 new points, this one here and this one here. And I'm going to call them B1. This will be B1 and this one will be B2. All right? And I'm going to declare that, okay, now we have a new vector, this one here, from B1 to B2. And we'll say that that's the same conic vector as the one that we started with, A1, A2. Now let's do the same kind of thing here and translate this vector again by doing the same kind of thing. We'll use parallel lines in a different direction. Maybe we'll go over in this direction here. Okay. maybe like this. Okay, so there's a line through B2 and a parallel line through B1, meeting the conic at two new points, which we can draw, label. That was B2, so we'll call this one C1. This was B1, we'll call this one C2. Okay. Now we have a new vector, this one here, and we're going to say that that's also the same vector V. And we are going to say that, okay, now we've translated this original vector V to this position. In fact, we've also translated it also around to this position. Now, the natural question when you do this is, wait a minute, is this actually consistent? Does the result of this translation depend on this intermediate choice? So what that amounts to is the question, well, suppose we started with these 2 points and we immediately tried to translate to C. So that would mean we would draw that line there between A2 and C1, and then we would draw a parallel line through A1 to C2, parallel to this one here. And as the diagram suggests, that would indeed give us exactly the same pair that we got this way. To put it another way, if these two lines are parallel and these two lines are parallel, then these two lines are also parallel. And that turns out to be exactly a special case of Pascal's theorem again. So right here, this is Pascal again. But it's a special case because it's a special case when the points of intersection of these lines are all at infinity in a projective setting. Okay, so these two lines meet at the line at infinity. These two lines meet at the line at infinity. So the line they determine is the line at infinity, and the consequence of the theorem is that this third pair of lines will necessarily also have to meet at infinity. In other words, also be parallel. So it turns out that Lemmermeyer's product gives us a well-defined notion of vectors on a conic, and we're able to translate those vectors. And once we can translate vectors, well, then we can add them, because we just take one vector and move the second one so that it's starting at the head of the first vector, and then that combined thing will be the sum of those two vectors. This means we can also take a vector v and we can multiply it by 2 or by 3. But crucially, what we cannot do is we cannot divide. Okay? We are not able to divide a vector by 2 or 3 or 4 or 5. That's why I say it's an integral affine structure. So it's a little bit different from over here. Over here we are able to, just using parallel lines, subdivide a vector into any number of equal pieces. Not so here. There's a very important distinction. Okay? So we're getting an integral affine structure on a conic. And I think this is a new kind of point of view, and it's worth thinking about. It's quite a general thing that applies both to ellipses, parabolas, and hyperbolas. Once we have these ideas in our minds, we can use them to generate what we might call a ladder. So a ladder is a sequence of points which are all generated by the same process, essentially doing a Lemmermeyer kind of product. So tangents are involved here. So what we do is we start with 2 points, say A0 and A1, on a conic C. And we want to extend that to a spline, A0, A1, A2, all the way up to AN for some n. And what we want is so that each of the successive points in this spline generate equal vectors, equal conic vectors, exactly in the sense we've just described. So we want the conic vector from A0 to A1 to equal the conic vector A1, A2, equals the conic vector A2, A3, etc. So how do we actually do that in practice? So that's like saying, okay, so we start with A0 and A1. How do we create A2 so that this vector from here to here is the same as this vector from here to here? Well, what we do is we take A0 and A1 and we look at the tangent to the conic at A1. Okay? And then we form a line through A0 which is parallel to that tangent at A1. Okay, so they're a bit close together here. So the tangent at A1 and then the line through A0 parallel to that will be just a little bit above it and will intersect at a new point A2. We keep doing the same thing. It's a little bit more visible up here. We have a little bit more curvature. So here's A4 and A5. If we want the next point in the ladder, go up one rung. We take the tangent at A5. We take the line through A4 parallel to that tangent, and we just see where the other point of intersection is. And that's going to be then A6. All right, so we just work our way up, tangent, parallel line, and get this sequence of points which are equally spaced in this conic vector point of view. As conic vectors, all these separations are equal. We can call this a ladder on the conic. So here's the ladder A0, A1, all the way up to A7 on a conic. Now we want to look at what actually happens when we take this general construction of Lemmermeyer and apply it to our three favorite geometries, the blue, red, and green. Interesting things happen. So let's start out with the blue, the familiar one where the unit circle, x squared plus y squared equals 1, is taking center place. That's the conic that we're interested in. And we're thinking about this as being the unit circle in the blue complex numbers. So there's 1 and there's I. Okay, so what we can do is we can generate a standard ladder. So that's one that starts with A0 being the point 1. Okay, so there's the point 1, and let's choose a point Z on the unit circle. And we're going to then define the subsequent points in the ladder to be just powers of Z in the blue complex number situation. So we're using complex number multiplication to multiply that point Z by itself repeated times. So if here is Z, then here is Z squared. And then Z cubed will be an equal amount around, and then Z to the fourth and so on, maybe all the way up to, say, Z to the n. Okay, so that's our definition of A sub k. It's Z to the k, and we're assuming that the Z that we're starting with is on the unit circle. In other words, its quadrants is equal to 1. It is then a fact that the sequence that we get is a ladder in the Lemmermeyer sense. In other words, that the group structure that Lemmermeyer discusses geometrically is exactly the same as the group structure occurring here algebraically via the complex numbers. To put it another way, to go from Z to Z squared, another way of thinking about what we're doing geometrically is we're taking the tangent at Z, taking the line through 1, which is parallel to that tangent, and seeing where the other meet is. That's very familiar because we're so familiar with the geometry of the circle. We can, in terms of angles, we say that angle is equal to that angle. But that's only an approximate story. We prefer not to use angles. We can just talk about the geometrical aspect in terms of either these tangents, that doesn't have any metrical structure, or algebraically in terms of squaring, cubing, taking powers of a fixed Z. So pleasantly, once you understood this situation, then it translates almost immediately to the red complex number story. So here's the red complex number. So instead of having an I, there's now a J there. I remind you that J squared is equal to 1. And here is the unit circle in the red story, the curve with the equation x squared minus y squared equals 1, what we sometimes call a relativistic hyperbola. Okay, so we can do the same thing. There's the number 1 lying on this hyperbola, and here is some point Z also on the hyperbola. So we can then form a ladder by taking powers of Z in the red complex number situation. So we write this as a combination of 1 and J, and we square it using the algebraic relation that J squared equals 1. Okay? So we get 1, there's Z, Z squared, then Z cubed will be further up, Z to the fourth will be even further out. they'll get increasingly far apart as the power increases. Actually, it's amusing to think what happens if z could also be on this branch. You can still do it. You can think about what's going to happen with the powers of z. So again, we have this correspondence between this algebraic description and the Lemmermeyer completely geometrical description. Another way of going from 1 and z to z squared is to take the tangent to the curve at z and draw the line through 1 parallel to that tangent. That's another way of getting the next one in the ladder. So we can use the algebra, or we can use the geometry just involving parallel lines. Both of them give us the same concept of a ladder, an integral ladder on the conic. So maybe this is all just warm-up for the case that we're really interested in, which is the green geometry, associated to our most important curve, this standard hyperbola xy equals 1, which we're starting to think about now as the circle, the unit circle in the green geometry. Okay, so we're thinking about the green complex plane. I remind you that in the green complex plane, this point here, the point 1, 1, is actually the identity, what we call the number 1. And the k is down here, but we don't need k for this. Okay, we're going to do the same thing as we did in the other cases. We're going to take a point z on our curve, and we're going to consider the points a sub k, which are just powers of z, but now with respect to the green algebra, the green complex number story. And I remind you that that's the simplest of the three algebraically, because the product of two vectors is just component-wise. You take the product of the two first entries, and you take the product of the two second entries, and that's all. So if here is, say, z, I'm actually choosing z to be, say, like 3/2, 1.5 x-coordinate, and then correspondingly it'll have to be 2/3 as y-coordinate. So if that is z, then there's z squared, and there's z cubed, there's z to the 4th. Here they are explicitly. So if z is this one here, 3/2, 2/3, then a0 is 1, which is the point 1, 1. a1 is that one. a2 will be this thing squared, so 3/2 squared, 2/3 squared. a3 will be this thing cubed, in other words 27 over 8 and 8 over 27. And a to the 4th will be the 4th powers, 81 over 16 and 16 over 81. Over 81. Okay, good. So those 5 points are going to give us a standard ladder. Standard just referring to the fact that starts with the point 1. A0, A1, A2, A3, A4. Great. Now, in this situation, the points have been described algebraically using powers in the green algebra. But the Lemmermeyer interpretation is still completely valid. To go from z and z squared to z cubed, we would take the tangent at z squared, draw the line parallel to the tangent through z, and see where the other point of intersection was. Now, multiplication by z. Multiplication by z moves us from one rung of the ladder to the next. Okay? So just to keep going, we're just multiplying by z each time. And this allows us to extend the thing to higher powers of z if we wanted to, but in fact also to negative powers of z. Because instead of multiplying by z, we could multiply by the inverse of z, which is just what you get when you flip those things around. In that case, z inverse would be up there somewhere, and z to the -2 would be up there. They would march up in that direction. So in this case, all the points on this ladder would be on this one branch of the hyperbola. There's actually another branch down here, which is not part of the story that we're talking about right now. Although we could start with a z over there, and then the thing would bounce back and forth. But I'm illustrating it for a z on this branch. But both algebraically and geometrically, the same would work no matter where z is. Now the general ladder in this case is just a shift of the standard kind of ladder that we've just described. So it has the form of a spline A0, A1, say up to AN, where now A sub k is u times z to the k for some pair of numbers u and z on the unit circle. So for example, in this case here, there's our number 1, there's our number z, same one actually that we were considering before. So z squared would be down here and z cubed and so on. But now here's a number u, and one way of thinking about what we're doing is we're taking this previous standard, the standard ladder generated by powers of z, and multiplying each one by u. Okay? And we get u in green, and then uz squared, uz cubed, uz to the fourth, etc. Another way of thinking about that is we're starting with u, and then we're multiplying by consecutive powers of z. So we just multiply by z each time. Z here is 1.5 and 2/3. So the x-coordinate is going to just be multiplied by 1.5 each time. So we take this x-coordinate, we take 1.5 of that, and that's the x-coordinate of u times z. Then again, we take 1.5 times that, and we get u of z squared, and then uz cubed, and then uz to the fourth, and so on. Okay, so here then is an important theorem that if we have such a unit circle ladder of this kind, so A0, A1 up to AN, then what happens is that the signed areas of each of the individual oriented edges of this spline are equal. Okay, so the signed area A0 to A1 equals the signed area of A1 to A2 equals the signed area all the way up to the A sub n minus 1 to A sub n. So then we get all these triangles formed by the origin and the points on the spline, and the claim is that the signed areas of each one of those triangles is actually equal. So it's just a triangle formed by that point, and that point. Okay. They're all the same. That triangle area, that triangle area, that triangle area, they're all the same. That's with straight line segments on the top. And the reason, well, the proof is that multiplication by z is a linear transformation. Right? What we're doing is we're applying a linear transformation, and this linear transformation has determinant q of z equals 1. Okay? And so that's why if you take one of these triangles, say the first one, and you multiply everything by z, well, then you're going to get the next triangle. So the linear transformation is such that the triangular areas are going to be exactly the same. And the beauty of this argument is that it doesn't really depend that we're in the green situation. Okay? This argument works also in the blue and in the red situation. So this is a general theorem that holds in all three geometries. And here's explicitly what the linear transformation is in the example that we're looking at. When z is 3/2 and 2/3, then multiplying by z, take a point xy or a vector xy, multiplying by z in the green complex number story just takes you to the point 3/2 x, 2/3 y. That's exactly a stretch in the x direction by 3/2 and a dilation by 2/3, and those exactly cancel out to have area, it's still area preserving. Now, very pleasantly, that argument about what happens when you multiply by z in the complex number situation extends. It extends to approx areas. So now we're going to move to a more applied setting where we're talking about concepts which have not been nailed down very precisely, about concepts of signed areas of curves like the green unit circle, or in fact the blue unit circle or the red unit circle, in terms of signed slice areas and signed cap areas. So these are things that we've talked only up till now in an approximate kind of informal fashion. But nevertheless, there's an important idea here that I want you to understand, okay? Which is that we're able to make conclusions about approximate areas under or determined by segments of such a curve. So suppose that u and z are gamma. Gamma is x, y equals 1. And for example, here is 1, and here is z, and here is u. And here's the product u times z. And let's say we consider multiplication by u. Okay? And multiplication by u is going to send this portion of the curve from 1 to z, that segment there, to the segment from u to uz. So multiplication by u preserves the quadrants. In other words, if a point is on this curve and we multiply by another point on the curve, we are still on the curve because the quadrants of product is the product of the quadrants. So that means that this segment here is actually mapped onto this segment here. So this multiplication by u has the effect of taking this sort of curved triangle from the origin to these 2 points with straight lines, and then the curve to the curved triangle with the origin and the points u and uz. Right? So exactly the same argument is telling us that this signed area, whatever it's going to be, of the curve gamma from, let's say, the point 1 to the point z. So we don't have a parameterization here, we just have the curve. So I'm just going to refer to this signed area in terms of the endpoints. Okay, so signed area from 1 to z of the curve gamma is going to be equal to the signed area from u to uz of the same curve gamma. And the same argument's going to apply to the signed slice areas and the signed cap areas. The corresponding signed slice areas are also going to be the same for this segment and for this segment. And the corresponding cap or signed cap areas are also going to be the same for both of these segments. And I remind you, sort of enlarging, let's say enlarge this thing here so we can see it a bit more clearly. There's the curve gamma, and there's the point u, and there's the point uz, and we've magnified things. Okay, so there's the chord between them. Then this green area here between the curve and the segment going this way. This is the signed slice area from u to uz of the curve gamma. While if we take the tangents at u and at uz, then the curve together with those two tangents is the red area there. That's the signed cap area from u to uz, both oriented in this case in that direction. So there's quotes here. These quantities have not been rigorously defined. Okay, they're only to be thought of in an approximate fashion at the present time. But nevertheless, the qualities here are kind of exact. In other words, that it's not that this is approximately equal to that. It's that any bound that you have for this thing will be a bound for this thing. Okay, so these two quantities, whatever they are going to act exactly the same in this sort of approximate setting. And so now we can introduce logarithms in this very general context. So this is a general context in the sense that the ideas are applying actually both to the blue and the red and the green stories. In the green story, we're getting the theory of logarithms. And in the other stories, well, it's relating to circular or hyperbolic functions. But it's a framework that actually encompasses all three at the same time. Okay. So the logarithm is a really important concept historically and computationally because it's a very powerful tool for arithmetic. And we want to see exactly why that is. Okay? The reason is because it's reducing multiplication to addition. That's the simple reason why logarithms are important. Multiplication is roughly hard, addition is roughly simple, and so we're reducing something that's hard to something that's simple. However, this story necessarily involves an element of approximation. This is not a technology that one can do exactly. There's no way of getting around that there's an approximate aspect to this. Historically, computationally, even today, okay? And that's part of the story. And it's all really just a direct consequence of the ideas that we've seen in today's lecture. So let's put those things together. Here is the same curve we've been talking about. There's gamma. But now we're restricting ourselves to just to this branch. Let's call it gamma plus. So we're talking about the portion of the curve for which, say, the x coordinates are all positive or the y coordinates are all positive. Okay? So we're ignoring this other branch here. We've got z and u. There are 2 points on the curve. And we know that the signed area from 1 to z of gamma, which is this region here, is equal to the signed area from u to uz of the same curve. That's this region here. Okay, that's again because multiplication by u preserves areas, and multiplication by u sends this area to this area. Okay, so now let's look at the signed area from 1 to uz. The big area from here all the way up to there, that big area there. Okay? That is equal to the signed area from 1 to u of the curve plus the signed area from u to uz. Okay, well, that's the signed area from 1 to u, but the signed area from u to uz, we've just said that's the same as the signed area from 1 to z. So we can replace this one with signed area from 1 to z of gamma. What's this telling us? Something very interesting, that the signed area from 1 to the product u times z, that signed area there, is the sum of the signed area of the curve from 1 to u plus the signed area from 1 to z. Crucially with a plus. There's a multiplication, there's a plus. So we can bring this connection into focus by introducing, for a point z on gamma plus, we're going to define log z. Okay, z is a point, not a number, it's a point. We're going to define log of z to be exactly this signed area of the curve gamma from 1 to z. So there's z. What is log of that point? It's the signed area here, which admittedly is just an approximate object, right? We don't know exactly what this is, but we have technology for sort of putting it in little intervals. So there's quotes about this definition. But the definition then allows us to restate what we've just done up here. Okay, we just completely restated by noticing that the left-hand side is now log of u times z. And here we have log of u, and here we have log of z. So the log of this product, u times z, is the log of u plus the log of z. And this is the fundamental property that Napier and Briggs, and there was also a Swiss fellow, Bourdieu, I think, who in the 17th century introduced logarithms as a computational device, basically to simplify multiplications and divisions. Okay? The idea is that, okay, we don't know how to get u of z, but we can maybe calculate log of u and calculate log of z, perhaps with help of some tables. Then we can perform this addition, and we can go backwards then using the tables to find out what u of z is by knowing what its log is. It's a very simple idea. And the way I framed it here is such that it really doesn't depend on us using this particular curve. Okay, we could do the same kind of thing for the unit circle in the blue and in the red stories. It's just that in this situation, the product of these 2 points is essentially an arithmetical product, because the way the green multiplication of points works is it's component-wise multiplication in x and y coordinates. So this product of points is really like an ordinary multiplication of numbers, actually 2 of them. Okay, so that means that this green version of it, even though it's just completely analogous to the blue and red versions, this is the most useful one because this particular product is closely connected with ordinary multiplication of numbers. Okay. So this turns out to be the key starting point of the theory of logarithms. very important development in the history of science. So there's much to learn. I'm Norman Wahlberger. Thanks for listening.